Right, so our last section for this term is going to be on graphing sine and cosine functions. Okay, we'll learn what the basic graphs look like, and then how we can change the basic graphs. Right, so looking at this as like a sine or cosine wave, this is actually a program that models sound frequencies. Some of the ways we can transform a wave is we can shift it, right, left and right. Okay, we're going to talk about that today. That's called a phase shift. Tomorrow and later on in the week, we'll talk a little about stretching it. Okay, that one's a little different because it's actually taking the graph and stretching it. And that would have an effect if we were to play this sound. And besides stretching it left and right, we can also stretch it. I'm sorry, instead of stretching up and down, we can stretch left and right. Okay, stretch or compress. Right. And the other transformation we can do, I can't show you on here, but I can show you here. We can take the basic graph and we can do something like this. Right, so there's the original. Okay, that's the basic graph before you do anything to change it. And that +3 I put on the end, it moved it up 3. All right. As far as sound, there's no real connection between what I just did on this picture and sound. That's why I can't show you with the frequency program. All right. So those are the 4 transformations we'll look at. Moving up and down is 1, left and right is 2, stretching up and down is 3, and then stretching left and right is 4. Okay. Today and Thursday we'll do 1 transformation. Wednesday we'll do 2 of them. All right. Wednesdays are pretty easy to do. And the only 2 graphs that we're going to study this week are sine and cosine. What other trig function do we have a button for on the calculator that we used a lot last week? Tangent. Okay. We're not going to be looking at the graph of tangent. Okay. In pre-calculus, we look at that. In intro to trig, there isn't really enough time in just a 3-day lesson to kind of look at all that stuff. But I can show you a picture of tangent just so you don't feel left out and sad. Okay, there's a pattern to it, but one thing you might notice is it's not connected. Okay, it's not a nice wave. If you were going to draw it, you'd have to pick up your pencil each time you sketch a new part of the curve. With sine and cosine, you never lift your pencil. Okay, it's sine and cosine are what we call continuous. Okay, this is discontinuous because you have to lift up your pencil. Still a pattern to it, but not something we're going to look at in this class. All right, so the 2 we are going to look at, sine and cosine, okay, they're a special category of functions. So is tangent, but again, we're not studying it, called periodic functions. Okay, basically, what a periodic function means is it repeats itself. Okay. After you've sketched one part of this graph, if you continue to sketch it, you're repeating what you've already sketched before. Okay, so periodic functions repeat themselves. Right? And there's a certain number of x values we have to go through before it'll start repeating itself. Okay, so what I'll do is put up a picture of sine. Right? And let's graph it in, just to make it simple, I'm going to do the graph in degrees. I'm going to start at 0. And I'm going to end at 360. Okay, what you're looking at, or you will be in a second, that's what we call 1 full period of the sine function. Okay, it starts at 0, it goes up, it goes down, and it ends back at 0. If I were to continue sketching it, it would look just like this. This part of the graph just keeps repeating itself. So if you wanted to sketch instead of just one section, if you wanted to sketch 2 of them, It's hard for me to exactly line them up because there's a little border. But the idea is if I could connect them, that's what it would look like. That section just repeats itself. Does anybody remember what I set my window at? I started at 0, and what number did I end at? 360. Okay, the highest x value on this screen is from 0 to 360. That interval from 0 to 360 is how many degrees you have to go through before the graph repeats itself. Think of a circle. If you start at a point and you go all the way around, you get back where you started, and then it repeats. You can just keep going around the circle. And that interval before a function repeats itself is called its period. Here's another graph, a little bit more compressed. From here to there is one period. Goes up, goes down, goes back up, and then it would just start doing that pattern again. If you don't change the function at all, if you don't stretch it, you don't move it, just graph the basic function, it takes 2 pi radians or 360 degrees before it repeats itself. Okay, a lot of what we do this week is going to be in radians, so we'll get used to just putting things in radians, but I put degrees there just to help you out a little bit. So if the period is from 0 to 360, what do you think would happen if I only graph on the screen 0 to 180? What if I don't show all the way to 360? What do you think it'll look like?
Would it just say above the x-axis or below it, like one way or the other? Like it won't move through and go.
Yeah, it's not going to show the whole thing. It's only going to show the first half of it. Okay? So to see the whole thing, you have to go all the way from 0 to 360 on the x-axis. If you only go from 0 to 180, you're only getting the first half of the picture. Right? You're getting that top part right here. If you want to get the other half of the period, you've got to go all the way to 360. Okay? And that's important to remember. Okay? 360 or 2 pi. Right? So if I have you sketch a graph from 0 to 2 pi, all that's going to happen after 2 pi is the graph is going to repeat itself. Okay? Which is why when we do a sketch, we're not going to sketch it the way I have in green here. Okay? You're only going to have to sketch what's in blue. You're only going to sketch one period. Okay? Because I know what's going to happen after that. It's just going to repeat what you already did. And this could say sine or cosine. If you graph y equals cosine x, after 2 pi, the graph repeats itself. Okay, and another name for a period you might see in the book, or especially in other subject areas, they call it a cycle. One cycle of the graph. Right? We're going to refer to it usually as the period of the graph. Does anybody know where the word cycle is used? And specifically, it's used cycles per second. Anybody know what's measured in cycles per second? Something we use, probably most of us, I would think, use every day. Yeah? What do you mean? Well, RPMs are revolutions per minute. So this is a little different. This is cycles. I'm thinking of something that's measured in cycles per second. Okay. In fact, measuring something in cycles per second is so popular, it's named, there's a name they usually give it. It's named after someone. Anybody know what that is? Yeah?
Hertz.
Hertz. Okay, it's named after, I forget the guy's first name, but his last name was Hertz. All right, so now that I told you it's called Hertz, does anybody know what you measure in Hertz? There's a few things you can measure in Hertz. Yep.
Computer processors.
Yeah. A computer processor might run at like 2.4 gigahertz. If you got a microwave, they tell you it can interfere with cordless phones because sometimes a cordless phone and a microwave operate on the same megahertz frequency. Anybody know anything else you measure in hertz? Yeah. Yeah. If you saw it on the sound frequency generator, hertz, right there. That's the unit, or that's the it's the label that you use to describe a frequency, how high or low pitch it is, how many hertz. Another thing we use it for is electricity. Okay, if you had a multimeter and you measure the electricity in any of the outlets in this room, okay, it should be running at 60 hertz. Okay, 60 hertz. That's the frequency of current in the United States. That's why if you go to other countries, you can't just plug in something that's not made to work on different kind of electricity. Okay, like in Europe, they usually use 50 hertz. Okay, so if you go to plug in your computer and it's not designed for 50 hertz, you'll ruin it. Okay, because the frequency is a little different. If you look at your cell phone charger, it says it on it. Okay, sometimes just look at it when you plug it in. It says on it the voltage it's made for, and it says the frequency it's made for. When I went to Europe, it wasn't a problem because everything I have is relatively new, so the new transformers are designed to work on any electricity. You can use 60 hertz, 50 hertz, doesn't matter. The transformer figures it out for you. But older things weren't made to work, so you had to be careful. Right. So it's a unit we use a lot. We won't get into electricity too much, but we will get into some stuff with sound. All right, so basically to graph a sine or cosine function, you need 5 points. Okay, I call them the 5 critical points or the 5 key points for the graph. Okay, we like to know where it starts, where it stops, what's right in the middle, the highest and the lowest. You could get more points if you want, but I think 5 is sufficient. It's enough points that you can make the picture and get an accurate sketch. And since we're not sketching additional periods, you don't need more points. Okay? If I was going to sketch another period on the end of this, well, then I might want to find a 6th, 7th, 8th, and 9th point. Okay? But I'm not sketching beyond one period, so I'm not going to worry about that. All right, so far, all the information I'm giving you is just general information about periodic functions. Okay? In a second, we're going to start talking specifically about one transformation that we're going to do this week, and that's phase shift. Okay? But anytime you want to do a transformation, doesn't matter if it's a phase shift, which is what we're going to do today, or anything else that we learn tomorrow and Thursday. We always have to start with these 2 tables. Okay? These 2 tables are your starting point for every transformation. If you don't know where to start, you can't figure out where to go to. Right? So an example might be, I'll say, take the sine function and shift it up 2 units. Well, if you don't know where it starts, you can't figure out how to go up 2. You've got to know where to start from. So this is where you start from. Okay, and these 5 points are all equally spaced. Okay, if I wrote them out in degrees, just to show you, that's 0. How about pi over 2? Anybody remember how many degrees that is? 90. How about pi? Yep, pi is 180. Well, if pi is 180, if you double 2 pi, that's 360. And how about 3 pi over 2? 270. So these points are spaced every 90 degrees. 0, 90, 180, 270, 360. We got to get used to not seeing them in degrees, though. And let's look at the graph of sine and see if that table makes sense. Let's do it in radians. So I'm going to start at 0, and in degrees, I have to end at 360. What's that the same as in radians? 2 pi. We're going to end at 2 pi. Did anybody notice the highest and the lowest that the sine function went? When we had those pictures? It didn't go up forever. It kind of hit a maximum value, and then it started coming back down. Yeah. And we've talked a little about this last week. Okay. The highest it goes is 1, and the lowest is -1. Right? And you can see it pretty clearly on the screen right there. Right. So if you look at this table, it should make sense with that picture. When x is 0, y is 0. You're right there. When you're at 90 degrees, that's right here. That's the highest value you ever hit, or 1. When you get to pi, you're back at 0. 270 is right there. That's the lowest. And 360, or 2 pi, that's back to 0. Okay, so that's your table for sine. All right, let's put cosine up at the same time. I don't think we've looked at that one yet. Anybody see the difference between sine and cosine? Yeah, they're just shifts of each other. If you take sine and move it to the left, or take the red one and move it to the right, either way, they would line up perfectly. Right? So you're going to see all the same values for cosine, same x values. Now for cosine, it starts at its highest value, 1. Then it comes down to 0, -1, 0, back to 1. Those are the values in the table. Starts at 1, comes down to 0, hits its lowest value, comes back up to 0, and then it always ends where it starts. Right, so anytime we're talking about a cosine function, and I want you to do something to it, move it up, move it down, just do something, you have to start with this table, the one on the right. Anytime I want to do something with a sine function, start with the one on the left. Okay, a mistake I usually see is people, they do everything right, but they just start with the wrong table. Like we'll do a sine function, and for some reason people start with the cosine table. Just make a mistake. Right. Does everybody have these two tables? All right. Okay. And the way we're going to do transformations, we're going to keep it pretty straightforward. We're only going to do one transformation at a time. So in other words, I'm never going to give you a problem and say, I want you to shift it up and left. That's two things. I'll give you a problem and I'll say, we're going to shift it up, and that's it. Or we're going to shift left, and that's it. Okay? We're not going to do two things at the same time. So what that means is when you transform it, one of the columns I just gave you in those tables isn't going to change. Let me show you an example. If I were to shift something up, what axis does that affect if you move up? It affects y values. Okay? If you move up, it doesn't do anything left and right. Okay? X values are not affected when you shift something up. So for the example I just gave you, shift up. The x values are not going to change. You can go back to your original table and copy them down. The only thing that's going to change if you shift something up or down are the y, are the y values. So we'll have to figure out how do we find those. Okay, but my point is that in every transformation we do, one of these columns is going to stay the same, either the x's or the y's, and the other column will change. Okay, any questions on that idea? And it's not that it's impossible to do two transformations at the same time. In pre-calc, sometimes I have them do three things at the same time. You say shift it up, shift it left, and then stretch it out. Okay? But we're not getting into functions that much, and we only really have 3 days, so we're just going to look at the basic ones. All right, so now everything I give you for the rest of today is about a phase shift. All right, that's what we're saying. So phase shift. So the transformation we're going to look at today is called a phase shift, and that's when you move the graph left or right. So as an example, if I use my sound frequency program, what I just did was a phase shift. It just takes the graph, it doesn't stretch it in any way. It just pushes it left or right. And we'll hear what that sounds like in a little bit. Okay. So now that we know what a phase shift is, it's when things move left and right, we have to look at, when we write that as an equation, what does a phase shift look like? And this is what it looks like. It's when you have sine or cosine, and you add or subtract something inside the parentheses. Okay? That's what makes it a phase shift. Okay? It's when you add or subtract a number inside the parentheses. Hey, and just to show you, well, what could you do that's different? Let me show you, I'll show you all four of them. Okay, this is a phase shift. Sine of x plus pi. Okay, we're going to do one like that today. This is a vertical shift. Okay, we're not studying this transformation today, but you might guess this one shifts a graph up and down. Okay, with a vertical shift, it still adds something, but the difference is what you add is outside the parentheses. Okay, we're going to study that one tomorrow. So those are shifting. What else can we do? Let's do a vertical stretch. Okay, that looks something like this. Okay, it's all where you put the number. Okay? In this case, with a vertical stretch, you put the number in front. Okay? So we're not adding something inside the parentheses. We're not adding something on the end. We're multiplying by a number in front. We're not studying this one today either. Okay? Just showing you the different ones we're going to study. And the last one is a period change. That one looks like this. Okay, we are multiplying. We're multiplying the 3 by something, but now we're multiplying inside the parentheses instead of in front. Right, so my point showing you those 3 examples is not to memorize, what's what yet, just to show you it makes a big difference where you put the number. Okay, and this is what we're going to look at today. Right, but that's a good chart, a good reference sheet to come back to. So if you have to identify, is this a vertical shift or is this a vertical stretch? Okay, you got an example of each one of them. And we'll do more throughout the week. All right, so out of the 4 transformations, there's 2 of them that do exactly what you would think, and there's 2 of them that do the opposite of what you would think. Okay, phase shift is one of the transformations that does the opposite of what you would think. And if you follow these directions, that's all you have to worry about. If you do x and subtract inside the parentheses. Okay, in the example I gave you, I added. Okay, so that's different direction. But if you subtract inside the parentheses, that causes your graph to shift right. So subtracting inside parentheses causes your graph to shift right. How much does it shift by? Well, it depends on what you subtract. If you subtract 5, it would shift 5 units. If you subtract 50, it would shift 50 units. You can shift it any amount you want. Generally, there are common shifts that we do, and we're going to stick with those. Usually we shift something by 180 degrees, 90 degrees, or 45 degrees. Again, there's no reason why you can't shift it by 32.4 degrees if that makes you happy. But we're not going to do that. Okay, we'll stick with numbers that we're used to working with, like 45, 90, and 180. So what do you think is going to happen if I do x and then plus a number inside parentheses? That's like this example, x plus pi. What direction do you think that's going to shift? To which way? To the right? Well, if we do x minus, that's going to shift right.
Outer.
So if we do plus, it's going to shift the other way, which is to the left. You might think, well, why? When you go plus, like if you think of like your number line,
Yeah.
the positive numbers go to the right, the negatives go to the left. It just doesn't work that way with phase shift. Right, and I also have this on the worksheet. Tonight's homework will be it'll be a worksheet, and this is written on it. So if you forget which way something shifts, minus shifts right, plus shifts left. And again, you can shift it however much you want, but we're going to stick with shifting it by common amounts. 45, 90, 180. Okay, except we're going to do it in radians. Okay. Any questions on that? Right, so last thing we have to figure out before we do an example is the 5 points. Okay, and then we'll start making some graphs. All right, so we're doing a phase shift. Wes, can you remind me again, what direction does a phase shift move the graph?
Phase shift is right, I believe.
Right or
Right or left.
or left. Okay, it's going to move it horizontally. What values are affected when you move things horizontally?
X value.
Those are your x values. Okay, your x values are affected. So when you move horizontally, what values don't change?
Y.
The y's. Right, so for a phase shift, what we're going to do, we're going to write down our 5 points. But to get the y values, we're going to go back to those 2 original tables I gave you, and we're just going to copy down what's in them. The y values will not change from those original tables for every single problem we do today. Because we are going to move things left and right. That only affects the x's. All right, so if the y's are going to stay the same, then the x's are what is going to change. All right, so how do we get the new x's? Well, look at what's been added or subtracted. Okay, in the example we're about to do, I'm subtracting pi over 2. Okay, so we're going to look at what's been added or subtracted. In that example, it was minus pi over 2. And we have to do the opposite. Why do we have to do the opposite? That's just the way phase shift works. Okay. So find what's been added or subtracted and do the opposite of that to all the original x's in your table. And once we go through an example, I think it'll be a lot clearer. It's not as hard as it seems. So let's leave that up. Okay. On your homework, it's already got a grid drawn for you, so you're not going to have to make grids yourself or use graph paper. Okay. It's already right on there. Right, so our first problem says to graph y equals sine x minus pi over 2. If at this point I knew about every transformation, the first thing I'd have to do is figure out what is this? If there's 4 choices, in this case it's a phase shift. Okay, so on a test or a quiz, that would be step 1. Figure out, is it a phase shift, vertical stretch, or period change? Well, I know it's a phase shift because that's when you add or subtract inside the parentheses. Right, so Ashley, since it's a phase shift, what direction is this graph potentially going to move in? Left, or it could move right. Okay. The point is, it's going to move horizontally. So our x's are going to change. We're moving horizontally. So Bailey, what value does that mean are going to stay the same?
The y's.
The y's. Okay. What I've done is I already copied down the original table you had in your notes right here. Okay. I'm not going to do that for every problem, but for the first one I did. Copy down the y values into a new table. Right, so we got 0, 1, 0, -1, 0. Okay, on a test, the way I grade that is I give you 1 point for each x and y value you get right in the table. So you'd get 5 points just for copying those numbers right. Okay, any questions why the y values are staying the same? All right, now we got to figure out what's going to happen to the x values. Okay, x values do not stay the same. So look at what's been added or subtracted, and we're going to do the opposite of that to all my original x's. Right, Kate, in this case, have I added or subtracted? So in this case, I subtracted pi over 2. So do the opposite of that to all the original x's. So we've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, I'm just copying my originals. And Kate just said add pi over 2 to all of them. Why? Because that's how you do a phase shift. You add or subtract something to the x's.
Now, why do you choose to add those?
Because we always have to do the opposite.
Oh.
That's just the way a phase shift works. Which is why it can be tricky. They don't all work that way, but phase shift does. Okay, so add pi over 2, add pi over 2, add pi over 2. Okay, and what I'm going to be grading is what we put for answers inside that box. Right, so now we just have to do out what I wrote down. Okay, what's 0 plus pi over 2? Just pi over 2. Okay, another point for that one. What's pi over 2 plus pi over 2? Yep, 2 pi over 2, which reduces to just pi. Okay, the next one, pi plus pi over 2. Well, right now, let's look at how, if we try to add those up, what's going to happen? There's no denominator on pi, so what is it? It's a 1. So to add these together, we have to make those denominators the same. What's the common denominator between 1 and 2? 2. So how do you change 1 into 2? What do you multiply it by? 2. So if you multiply the bottom by 2, what else do you have to do? Multiply the top by 2. 2 pi over 2 plus 1 pi over 2. What's that? Oh, Jason? Two pi over 2 plus 1 pi over 2. Think of it as 2 over 2 plus 1 over 2. What did you say the first time? 3 over 2. Yeah. The only thing is we have a pi on the top as well, so it's 3 pi over 2. Okay, how about 3 pi over 2 plus 4 pi, 3 pi over 2 plus 1 pi over 2?
4 pi over 2.
4 pi over 2, which becomes 2 pi. And the last one, 2, what is it?
3 pi over 2.
Yep, we got 3 pi over 2. That was the one we did before. Now we've got 2 pi plus pi over 2. What's our common denominator? 2?
Yeah. So it's 5 pi over 2.
Yeah. So it's 4 pi over 2 plus 1 pi over 2. That's 5 pi over 2. Now, if you hadn't reduced things as we went along, okay, I do want you to reduce things like this. You would have noticed a pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. You always get a nice pattern. If we were going to keep going, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. But we're not going to keep going. Okay, we stop there. Okay, any questions on how we got that table? All right, so that's our table. And the last thing is just make our sketch. Okay, the table, on a test, the table is worth 10 points. Okay, 1 point for each x and y value. The picture itself is only worth like 1 or 2 points. All right, so we got the point pi over 2, 0. All right, so let's label our x-axis. And I'm going to label it with these numbers. Okay? Don't label it 1, 2, 3, 4, 5, because all these numbers are awful to work with. 3.1, 6.28, right? So we're going to label our x-axis with the numbers we have. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2.
So all you gotta do is just copy what's on the
Yep, exactly. We just use those numbers. You can label your x-axis any way you want.
Do you do that every time? Or?
Do I always use pi over 2 pi?
No, do you always just take whatever is on, whatever we have the coordinates and just put it right on the graphic?
Yeah, we always use those. Yep. Because you can label your x-axis with any numbers you want. You just have to keep it consistent. Okay? And we already said these are all nicely spaced. 90, 180, 270, 360, 450. They're all 90 degrees apart. Right, and that's going to be 1. And that's negative 1. All right, so we got pi over 2, 0. Pi, we're at 1. 3 pi over 2, back to 0. 2 pi, we're at negative 1. And 5 pi over 2, we're at 0. So maybe I should have put a couple of these labels up above so I didn't draw through them, but a lot of times you end up drawing through your labels. That's how it works. And that's your sketch. It doesn't have to be perfect, but try to make it curved. Okay, these graphs shouldn't have any sharp points to them. Okay, like if you did something like that, try to round those top and bottom off a little bit. Okay. And that's a phase shift. Okay. The original would have been right about there. It would have started at 0, 1, 0, negative 1, 0. Now it's been shifted to the right. Any questions on that? Okay, so what I'm going to have you do on the homework is I'm going to have you sketch the one in red, okay, separate. You don't have to do them on the same graph because that can look confusing. I'll have you sketch the one in red on the left, the one in black on the right, so you can see the transformation. If you want to sketch them both on the same axis like that, that's fine too. That's the original. That's the new one. All right, let's try another phase shift. All right, anybody tell me what's one thing that's really different about this one? We got to be careful when we go back and look at our original tables. Okay, we're adding, so it's going to shift in a different direction this time. And what else is really different? It's cosine. Okay, so forget about the sine table. Okay, this problem is about cosine. Nope, you should have two different tables for the original tables. That's the table you should have for sine. That's the table for cosine. All right, first question. Who can tell me, how do I know that's a phase shift? Because it's adding, that's a good part of it. And what else? It's adding where? In the parentheses. Yep. So that tells me it's a phase shift. Okay, now that we know it's a phase shift, what values never change when you do a phase shift? The y's. Okay, y's are going to stay the same. I need my 5 y values from the cosine table. Okay. Somebody remind me what those values are? Yeah?
1, 0, 1, 0, 1.
Yeah. Okay, so that's half our points right there. Okay, now I'm going to take all my original x's and I'm going to add or subtract something to them. In this case, am I going to add or am I going to subtract? Yep. And I'm going to subtract, and that was my next question. What do I subtract? And it is pi. Okay, so just for reference, I'm going to put the originals. Pi over 2, pi, 3 pi over 2, 2 pi. And then as Cade said, minus pi from all of them. Minus pi, minus pi, minus pi. Okay, and we'll put our answers in that box. Okay, some are easier than others. Sometimes you don't need a common denominator. Sometimes you do. Let's start with the first one. What's 0 minus pi? Negative. Yep. Let's do the third one. What's pi minus pi? 0. What's 2 pi take away 1 pi? Just 1 pi. Okay. There's no reason why I did those first. It's just they were the quickest ones to do in my head. Yeah. Okay, next one. Pi over 2 take away pi over 1. What do I need to do in order to subtract those? Yep. Common denominator. This time it's going to be 2. Double the bottom. Double the top. What's 1 pi over 2? Take away 2 pi over 2. Negative 1 pi over 2. Okay, let's do it one more time. 3 pi over 2. Take away pi over 1. Common denominator again. double the bottom, double the top. 3 pi over 2, take away 1 pi over 2. Pi over 2. Now, because everything doesn't have a denominator of 2, we don't see a pattern, but there is a pattern here. The first one is negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2. If we kept going, it would be 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. Okay, so that's our pattern. All right, so one point for each x and y value, so 10 points for that table, and then 2 points for making our picture. All right, this time we do need to go on to the negative axis. Okay, so we've got negative pi over 2. 0 you don't have to label. I'll assume that the axis is 0. Pi over 2 and pi. All right, so negative pi, we're up at 1, 0, negative 1, 0, and 1. Okay, this part of the graph is the one that people usually don't draw as well. They make it like a V. Okay, but remember, it's part of a curve that does something like this. So it does look kind of like a V, but try to give it a little bit of a curve to it. Okay. Any question on that one? All right, and before we look at our last one, let me play a phase shift on the frequency generator so you can hear what it sounds like, and then we'll finish up with our last example. All right, so each transformation that we learned is going to do something different to the sound. Does anybody have a guess what a phase shift is going to do to the sound? Yeah?
It'll eventually cancel it.
It'll cancel it out. Yes, that's exactly what happens. Basically, with a phase shift, it's going to sound like it's a change in volume, but I'm not going to do anything to the volume slider. Okay? That's the volume slider I'm moving right now. But what happens is when you start to do a phase shift, you're going to hear it get quieter, and then all of a sudden, it's just going to disappear. Right, so I'm going to play. Okay, we'll play that frequency, and I'm going to slowly just change the phase of one of the two channels. If I line it up just right, I don't have it quite perfect, but if I line it up just right, you'd hear these two waves canceling each other out. Okay, and it got very, very soft. Notice I didn't do anything to change the volume on the computer, and I didn't do anything to change the volume on the frequency generator. It's the two waves actually canceling each other out. Right? And some places you see that used as like high-end cars. They basically cancel out engine noise by using other sound frequencies. Okay, I don't understand 100% how it works, but they cancel out sound with other sounds. Noise canceling headphones, okay, same idea. You can cancel out certain frequencies based on doing something just like that. Okay. So, any questions on what a phase shift sounds like? Okay, so basically the sound cancels out. And it makes sense that when they're lined up exactly like this, they're perfectly out of phase. As they start to come back in phase, then you start to hear it again. Notice there's no difference between a 0-degree phase shift and a 360-degree phase shift. They're the exact same picture. Can't tell the difference. That's why they sound the same. Okay, so any questions on that? All right, so phase shift, I don't think it's the most interesting one to hear. We can do a lot more when we start getting into frequency changes. And on Thursday, I'll show you something neat with frequency changes. Okay, and cell phones and stuff like that. All right. Last example, let's take a look at sine of x minus pi over 4. Okay, first I know it's a phase shift because I'm subtracting in parentheses. So my first question, what stays the same? The y's. Okay. Now we're doing sine. Okay, so Carter, can you remind me, what are my y values for sine?
0, 1, 0, negative 1, 0.
Yep. And now we're going to take all the original x's, which are 0, pi over 2, pi, 3 pi over 2, 2 pi. And Amy, am I going to add something to all of these or subtract? Yep, we're going to add. And John, can you tell me what I'm going to add?
Is it pi 2?
Not pi over 2 in this case.
Oh, pi.
Pi over 4, yeah. Okay, so we're going to add pi over 4. Let's see what we got. Okay, first one's pretty straightforward. 0 plus pi over 4 is pi over 4. Okay, next one. Pi over 2 plus pi over 4. Common denominator there. How about, Becca, what's my common denominator?
4.
4? And what would you multiply 2 by to make it 4?
2.
Yep, so do it to the bottom, do it to the top. So we get 2 pi over 2 plus 1 pi, I'm sorry, 2 pi over 4 plus 1 pi over 4. 2 plus 1 gives me 3 pi over 4. Okay, next one. Pi over 1 plus pi over 4. Common denominator here, Bailey?
4.
4. So what would you multiply 1 by?
4.
And the top?
4, 2.
By 4. What's 4 pi over 4 plus 1 pi over 4?
5 pi over 4.
5 pi over 4. Now, at this point, you might see the pattern. If you see the pattern, just go with the pattern. Does anybody think they know what the next one's going to be? Yep, 7 pi over 4. And how about the last one? 9 pi over 4. If you don't see the pattern, just do the common denominators again, and you can get the answer that way. But the pattern here, it's basically odd numbers in the numerator. Okay. So again, 1 point for each x and y value. And lastly, we'll just graph it, and that'll be it. All right, so we've got pi over 4. Now, if you want to space it out more, because you're like, you know what, things are just too cramped for me, you can space it out more. If you just skip consistently. Okay, show you how you can, if you want to space it out more. Let's just see if I can just move my axis over. All right, let's have my axis start here. Move those with it. And just draw that in. All right, so I can have that be 0. And let's have this one be pi over 4. Now, the only thing is if I skip once, I have to skip every time. So skip 3 pi over 4, skip 5 pi over 4, skip 7 pi over 4. And what else do I need? I need one more. Skip, and then 9 pi over 4. Okay, would I skip on this one? Probably not. I don't really think there's a need to. But if you want to space things out, you can. Just make sure you're consistent. Don't skip one time and then not skip the next time. Okay, just be consistent. Let's make that 1 and negative 1. And graph it. All right, so pi over 4, we are at 0. 3 pi over 4, go up to 1. 5 pi over 4 back to 0. Negative 1, which unfortunately it's right in the middle of my label, but hold on. And back to 0. And connect it. Should be a little easier on the homework because the graph paper is already drawn for you. Any questions on that one? Okay, so that's a phase shift. Just moving the graph left and right. If you have a graphing calculator, you can also look at phase shifts on there as well. Okay, questions on that last one? All right, so homework tonight, it's going to be a worksheet. It's going to be a worksheet all week. So you don't need your book this week at all. There's 5 questions to graph. Okay, there's a spot for you to show me the original, and then show me the transformed graph.